This lesson we're going to be looking at linear approximations. The idea behind a linear approximation is if we have some function, let's say we have this function y equals f of x, we could actually use a tangent line to the curve of f of x at a to approximate values for this function for values close to a. Let's say we wanted to approximate a value here, let's say, for this function. There's the actual function of, and let's call this value x equals a plus h. We could evaluate the function at f of a plus h, but we could also create the equation of this line, and let's call that line L of x. We could create the equation of this line and actually use the equation of this line to estimate values of the function. So if I say I'm going to plug in a plus h to my linear function, so I'd have L of a plus h, and I could plug that value in for x and use the equation of this line to approximate this value f of a plus h. Now you can see this would just be an estimate here for the actual value of f of a plus h. But sometimes it's easier to evaluate a function if you linearize the function around a point and use that linearization to find the value rather than plugging that value back into the original function. That's called a linear approximation. So the idea behind a linear approximation is we're going to find the equation of the tangent line at some value x equals a, and then we can use the equation of that line to estimate values of the function for values close to a. We could be down here less than a, getting values very close to a, but we are not going to use this linearization, let's say way out here for this value. That would not be a good estimate. Well, we could, if we wanted a value way out there, linearize the function at that point and then use the line for values close to, let's say that was b. Then we could use that equation of that line. So we find a point that we're interested in, and we may use points around that value, and we'll use the line to approximate those values instead of the function. So that's called linearization of a function. So keep that in mind as we're going through this process. Suppose that the temperature of a turkey is 50 degrees after it is stuffed, and you put the turkey into a 325-degree oven. After an hour, the meat thermometer indicates the temperature of the turkey is 93 degrees, and after 2 hours, it indicates 129 degrees. Predict the temperature of the turkey after 3 hours. Now let's just get a general feel for this problem. If I was to graph the data that was given in this problem, and I said this axis is time, this axis is temperature, it appears that at time 0 it says the turkey is 50 degrees after it's stuffed, and you put the turkey into a 325-degree oven. So at time 0 the turkey would be 50 degrees. Now, after an hour, it says the temperature indicates the turkey is 93 degrees. So here at time 0, we could plot that point. At time 1, 1 hour, it says the temperature is 93 degrees, so we could plot a point there. After 2 hours, it says it's 129 degrees. So maybe we're up here at 129. And if we thought about the graph of what's going on here, time versus temperature, temperature versus time, the maximum temperature that we would get to would be 325 degrees because the oven is set at 325 degrees. So if we kind of drew a graph through those points, it may look something like this, where it's starting to approach 325 degrees. Now we're asked to predict the temperature of the turkey after 3 hours. So what we're going to try to do is we're going to create we're trying to estimate the temperature of turkey at 3 hours. So we will take, and let's say I missed the point a little bit there, but let's say that's time equals 2. Could we create the equation of this tangent line at that point and then use that to estimate the temperature of the turkey at 3 hours? We can see there would be a little bit of an error. Looks like it'd be an overestimate a little bit. But that's the idea behind this problem. We're going to linearize this function at 2 so we can estimate the temperature at 3 hours. All right, so let T of T represent the temperature of the turkey. So that would be on our vertical axis that we had just drawn. And T in hours, that would be our horizontal axis. And here's the given information. T of 0 equals 50, T of 1 equals 93, T of 2 equals 129. Now we need to estimate the derivative of T of 2, of T prime of 2, because we're trying to create the equation of the tangent line at 2 hours. So thinking back to what we've done previously with discrete values, we could use the 2 points, well, we could use the point at 129 and T equals 1, or T of 1 equals 93 to get an estimate for the slope of the tangent line at 2. So this is how we'll estimate the slope of the tangent line when time equals 2 hours. So we would get 93 minus 129 all over -1. And that equals 36. So that's the slope, that's the estimate for the slope of the tangent line at t equals 2. Well, if we have the tangent line, the slope of the tangent line, we do have a point on the line at 2 hours. We know the temperature is 129, so there are 2 values we could use to find our y-intercept. So we could plug those in, and then we would have the equation of our line. Now, here we are actually just finding the actual temperature. Let me write here that if we used our, I'm going to call it L of x, we found the slope of our tangent line was 36, and we knew that at time equals 2, we had a slope of 36. Now, if we have L of 2 equals 36, which is our slope, and our x value would be 2 plus b, we should now be able to solve for b, the y-intercept. Well, L of 2 is our 129 equals 36 times 2, 72 plus b. So if we solve for b, we would have 129 minus our 72. So we have b equals 57. So the equation of our line, and I'm using L of x to represent the linearization, we have 36 times x plus our 57. All right, so there's the linearization, our 36x plus 57. Now, if we want to know what the temperature, the estimated temperature would be at 3 hours, we'd have 36 times 3 plus 57. So we'd have 108 plus 57. And that's where we're getting our 165 degrees. So that's where this came from here. If we went ahead and found the equation of the tangent line and then plugged in 3, we get 165 degrees. So that would be our estimate for the temperature at 3 hours. Now, we looked at this earlier and said, if we create the equation of the tangent line at 2, it's going to be an overestimate. So to get a little bit better estimate, we may say, if we graphed this out on graph paper and looked at the slope of that tangent line, we may be able to get a better approximation for the slope of the tangent line. Or we could say we know it's going to be a little bit less than 36. So here we're estimating, well, the slope of the tangent line may be 33. Therefore, we're going to use 33 instead of 36, and we would get an estimate of 162 degrees. There's just a graphical representation like I drew earlier. There would be the tangent line to the curve. And if we drew the curve on here, we can see that we were using the equation of this line here to estimate when t equals 3. We were using the equation of the tangent line to estimate the actual temperature of the turkey. Now, this is just an explanation of why we sometimes linearize a function at a particular point. Sometimes it's easier to calculate values of f of a using the tangent line instead of the curve itself. Because the function, it could be just a difficult function to work with. So this is how we found the linearization of our function. And we typically use L of x to represent the linearization of the function at x equals a. Find the linearization of the function, the square root of x plus 3 at a equals 1, and use it to approximate the numbers, the square root of 3.98 and the square root of 4.05. So we're going to linearize the function at a equals 1. So to linearize the function, we do need the derivative of the function. So let's find the derivative. So our f prime of x would be 1 divided by 2 times the square root of x plus 3. We know f of 1 equals 2, and then f prime of 1, we just found the derivative, so we could evaluate the derivative. That would be 1/4. So the linearization would be 7 divided by 4 plus x divided by 4. So what we're saying here is for values very close to 1, we could approximate the function, the square root of x plus 3, using the line 7/4 plus x over 4. Now this is only going to be for values very close to 1. We would use this linear approximation. Well, we're trying to approximate 3.98. So look at your equation here. What would x have to equal in order for this to be 3.98? Well, x would have to equal 0.98, and that's a value very close to 1. So the linearization should work well for estimating this value. So if we're going to let x equal 0.98, we would let x equal 0.98 on this side also. So we'd plug in 0.98 for x, and that would be our approximation for the square root of 3.98. And again, it's because we linearized this function around a equals 1. So this would be appropriate to use for values very close to 1. And 0.98 is very close to 1. So here we get the square root of 3.98 is approximately, we use the approximately equal to because this is an estimate. This is an estimate using the equation of the tangent line, would give us 1.995. And likewise for the square root of 4.05, in this case, x would equal 1.05. And just to verify, plug into your calculator the square of 3.9 the square root of 3.98 and see what you get. It should be a value very close to 1.995. For what values of x is the linear approximation accurate to within 0.5 and 0.1? Now, this is asking us to give values of x that we could plug into this linearization and have the actual answer be within 0.5 of our estimate. So like the last problem we just did, we plugged in for x, we plugged in 0.98. We could determine how close that was to the actual answer. And I asked you to do that on the last slide. Plug in the square root of 3.98 into your calculator and compare it to what we got using the linearization. But how could we determine the values of x that would give us an accuracy within 0.5? Well, thinking about this problem, we want to know if we have our x plus 3, the square root of x plus 3, we want to know when the difference between our linearization and the actual answer is within 0.5. Well, if we want to know when the difference is between 0.5, we would be subtracting these two to find how far off we are. So for instance, if I have this function and I've linearized it right here, and I'm trying to determine how far off this estimate is to the actual value, well, I would be looking at right in here, this is the difference between the linearization and the function itself. However, sometimes the linearization can be an overestimate or it can be an underestimate. So we would take the absolute value of this quantity and we want to know when it is less than 0.05. So if we could solve this inequality, that will give us the values of x for where we could plug those values of x in, and our answer will be within 0.5 of the actual value. So that's the idea behind this problem. So in order to do that, we're going to take the difference between the function and our linearization, and since it could be an overestimate or underestimate, we're going to use absolute value. But remember, absolute value inequalities, we can rewrite it. So we could rewrite it like this. Now, this skipped a step, so let me show you that step. This could actually be written as, if I take away the absolute values, I could say this. But that would be taking and removing the absolute values. So what it would actually be, let me just write it up here, would be less than the square root of x plus 3 minus the quantity, and this is the equation of our line, would be less than. And then we could take this quantity right here, and we could subtract that from both sides, from each interval in our inequality. So that's what we have right here. Now, how do we solve something that looks like this? Well, we could try to do it algebraically, or we could do it graphically. Let's look at this graphically. If we were to plug in each one of these intervals in our calculator, so for instance, in y sub 1, we could plug in the square root of x plus 3 minus 0.5. Y sub 2, we could plug in the equation of the line, 7/4 plus x divided by 4. Y sub 3, we could plug in the square root of x plus 3 plus 0.5. And then we want to see where the line is between these two outside functions. So let's take a look at this graphically. So we can see where the line is between those two functions, and we notice negative 2.66 to 8.66. So any value of x that we plug in between negative 2.66 and 8.66 to our linearization, the answer will be within 0.5 of the actual function at that value. All right, differentials. The idea behind linear approximations are sometimes used to help formulate the terminology and notation of differentials. There's a relationship between these two. So if y equals f of x, where f is a differentiable function, then the differential dx is an independent variable. The differential dy is then defined in terms of dx by the equation. Now this should look familiar. Doesn't it look like just the derivative? If we were to take the derivative of a function, let's say we have y equals f of x. We would say the derivative is dy dx equals f prime of x. And doesn't it look like we've just multiplied the dx to this side? That's not what's happening. We're not algebraically just manipulating it that way. This, when it's written in this manner, this is called the differential. And we're going to explore this a little bit, but this is just going to be the slope of a line, and this is going to be small incremental changes in the value of x. So it looks like this is just moving up the linearization of a point at the linearization of the line at a particular point. So we can see we have this feel that they are connected somehow, this linearization and the differential. But this form right here is called the differential form. So we have a dependent variable, and we said we have a independent variable. And we're going to look at this differential and the linearization geometrically to see how they're connected. All right, so here's the interpretation geometrically of a differential and linearization. Now here the red line represents the linearization of a function at some value x. We can see from P to S, that would be our change in x. And this distance is called delta y. The actual change in the y value of the function we call delta y. That's the actual change from x to x plus delta x. That's the actual change in the y value. Now let's call this point Q, and we're going to define now delta y, we're going to define dy, the differential, as the difference in the y value, but using the linearization for that estimate. So the directed distance from S to R could be represented by f prime of x dx equals dy. And that should make sense because f prime of x is the slope of that tangent line, and dx is small incremental changes in the x value. So we're moving up along the slope of that line, or the equation of that line. So dy is the amount the tangent line rises or falls, just depending on your original function. If it's an increasing function, we have that overestimate. If it's a decreasing function, we may have an underestimate. Delta y is the amount the curve actually rises or falls. So that's what's important here. You have to understand that delta y is the actual change in the y value of the function, and dy is an estimate of the change in the y value using the differential, but that was actually the linearization of the function at x. Compare the values of delta y and dy. So we have our function, and it gives us a change in the x value from 2 to 2.05, and then again from 2 to 2.01. So if we want to find delta y is the actual change in the y value from x equals, and we're going to start at 2 to x equals 2.05. We can do that actual calculation by plugging in the value of 2 to the function and plugging in the value of 2.05. So we would take f of 2.05 minus f of 2 to actually get the change in our y value. So finding those values, we're plugging in 2 and 2.05 to the function, and then we're going to subtract them, and we get 0.717625. That's the actual change in the y value. That's our delta y. Now what's the difference between delta y and dy? Well, dy, we're going to use the differential to estimate the change in the y values using the differential. So if we use the differential, we're going to get 0.7. Now here, this would be our f prime of 2 times our dx. Now, if we looked at f prime of x, let's go back up here. F prime of x would equal 3x squared plus 2x minus 2. So f prime of 2 would equal 3 times 2 squared plus 2 times 2 minus 2. And you can see that's what this is right here. Okay, that's our f prime of 2. And then we multiply that times the change in x. And the change in x from 2 to 2.05 would be 0.05. So this is the estimate in the change in the y value using the differential. This is delta y, which is the actual change in the y value. So that's how we use the differential to estimate the change in the y value. And if we did the same thing when x changes from 2 to 2.01, delta y, and then there's your dy. And again, you can see very close. The dy is a very good estimate for our delta y. And again, it's because that the values that we are using are very close to 2. We're looking at the change. If we went from 2 to 5, well, dy may not be a very good estimate for our delta y.